So, I guess let me take a quick poll of the class. Maybe not quite that dark. I'll go to sleep, much less all you all. Pardon? I think it was a little less dark than that. Yeah, it was sort of the intermediate setting, I think. Okay. Okay. Are you able to see? So let me take a quick poll here. I can go really fast through the rest of these introductory slides so we can get into some of the more fundamental stuff, or we can continue going at this pace through some of this motivational stuff and talking about how combustion problems, how these fundamental problems flow out of different real-world choices. So let me repeat that question. So I'm going to have you vote. We can either kind of blitz through the rest of this first part, go real fast, so we can start to get into the real fundamental stuff, or we can continue going at the current pace through this presentation, sort of setting the stage for how these fundamental combustion issues arise out of real-world issues. So how many vote for number 1? And how many vote for number 2? Oh man, it's like a dead tie. Okay, well, tell you what, I'll take an intermediate pace. I'll jump over these. So I guess I'll just jump over a bunch of slides here then. I'm going to try to take an intermediate pace. But I guess what I've tried to illustrate for you, and I'll do again in a couple more slides, is there's some really interesting trade-offs and challenges associated with developing combustion systems. So for example, the cost and complexity. I talked about how when you go to a premix design, which is motivated by the need to do low NOx, you need multiple nozzles and you need multiple fuel circuits so that you can vary the power of the system, so you can turn it down. Because otherwise, if you need a system where you can run not just at one power setting, but at medium power, like if you think about an aircraft engine, it has to idle, it has to take off, it's got to do all this stuff. And if you run just a premix system with one fuel circuit, that means that your fuel-air ratio is going to vary over a very, very large range. And so the way you deal with that is you have multiple circuits where maybe one of the circuit is always on and the other one's getting turned on and off. But that adds cost and complexity. So you can see how cost and complexity, NOx and turndown interact with each other in that example. Similarly, blow-off is always a concern with premix systems. So blow-off and NOx is always a trade-off. Combustion instabilities. I just talked about how combustion instabilities and NOx trade with each other, right? I said how premix systems are organ pipes, non-premix systems are mufflers. And so these issues are all trading off with each other. The other part around this is I haven't talked about alternative fuels, but lots of interesting applications around burning with different types of fuels. And so the kinds of issues that you have to worry about change with fuel composition, right? So this is I pulled this from some data from a company called Solar Turbines, which makes sort of mid-sized gas turbines. And this is kind of an overview of the different types of fuels that they use. These would be gaseous fuels, not liquid fuels for aircraft engines. But these would be gas fuels. And so this has the primary constituents here. And the Wabi index is basically a measure of the heating value. So, as you have more and more diluents in your fuel, you're going to reduce your Wabi index, right? You're going to, if you have a lot of carbon dioxide, for instance, or a lot of nitrogen in your fuel, the amount of energy you get per unit pound of fuel goes down. So, for example, associated gas. This is the gas that comes when you're from oil. When you're pulling oil out of the ground, there's a certain amount of gas that's associated with it, associated gas. And so you can see there's a certain amount of methane and some higher hydrocarbons, some higher alkanes, C2H6 and C3H8, and then C4 plus just means C4H10 and C6H plus, ... And then CO2. CO2 would be a diluent. Let's take a look at LNG, liquefied natural gas. So this would be gas, say, coming from Australia. Australia has some very large natural gas fields, and they've liquefied the gas, and they're selling it in Korea or in Japan. And so what does that consist of? Well, it's mostly methane, but it also can have some ethane and propane and carbon dioxide and nitrogen. If we look at refinery gas, so gas, if you're doing some sort of industrial process to make plastics or to make, to refine crude oil. You're adding hydrogen, or you're hydrogenating or dehydrogenating, you're adding or taking away hydrogen. So you can get some interesting off gases, and in some cases you can get really high hydrogen off gases. So you can see 40 to 60% hydrogen. You can see the higher hydrocarbons. Landfill gas, this is an interesting one. So when you have anaerobic decomposition of organic matter, you generate a lot of methane. But you also generate carbon dioxide. So landfill gas, and there's a lot of landfills around. We used to just vent this stuff into the atmosphere, but nowadays most landfills are capturing that natural gas, and they are, in many cases, burning it on site with either a reciprocating engine or a gas turbine engine. And one of the challenges there is you can see the calorific content is pretty lousy because it can be 40 to 60% carbon dioxide. With the balance being methane. Let's see. Yeah, and then just a bunch of other different types of gases. This is a plot that was from Rolls-Royce Canada, and Rolls-Royce Canada is now sold to Siemens. But this is for different types of natural gases that they were running their engines on. The x-axis is percentage of methane. The y-axis is percentage of everything that's not methane, that's a fuel. So C2+, so this would be C2H6, C3H8, C4H10, etc. And so if you have no diluents, you're going to be on this line right here. This is zero inerts. Well, they call them inerts. So this is 0% inert, this is 15, this is 35. So if you have no inerts, you're on this line, right? So 100, 0, or if you have 90% methane, that means you're 10% higher hydrocarbons. And so as you move this way off this line, that means you have an inert in the fuel. So this would be 15% inert, right? So 75 plus 10 is 85, the balance being inerts. And again, those inerts typically for natural gas are nitrogen and CO2. But this just shows you, in some cases they're looking at natural gases that have as much as 20 to 25% higher hydrocarbons. So these would be fuels with really high heating values, very high Wabi indexes. Any thoughts on how that might have an influence on your combustion system by having to 20% or 25% higher hydrocarbons relative to, say, 5%? Yeah. Well, let's say, okay. So if once the gas is put in the gas pipeline, they're gonna blend it such that you're gonna have a given flame temperature. Higher NOx, maybe? Yeah. So if you have prompt NOx, higher prompt NOx emissions. You might have liquid fuel dropout, I think is where you're getting to. So particularly once you start getting propane, you might have actually gobs of pure liquid. Actually, I'll show you a picture next what happens. The other thing that can happen is you get auto ignition. You auto-ignite easier as you have these higher hydrocarbons. Now, as you move in this direction, it's going to get harder to burn, right? Because it's lower heating value. We'll talk about this next, so we'll just jump over this. Well, let's just hit these real quick. I talked about what makes a good combustion system. So these next slides, each one of them talks through those a little bit more detail, and I'm going to go through this quickly because I've already talked about this. So combustion instabilities. This is one of the challenges then that you run into. And what happens in a combustion instability is you get large amplitude acoustic waves. Like I said, the flame's making sound. If it's a premix system, it's now in a resonator. Rather than a muffler, it's in a resonator. And so this is actually a large eddy simulation from one of my colleagues showing the yellow is an instantaneous picture of the flame. The blue is vorticity contours. What happens is you get these large amplitude acoustic pulsations which trigger vortex shedding, and these vortices disturb the flame, they roll up the flame, they cause more heat release oscillation. And when the heat release oscillates, you get more sound. And so this is a picture of if you were to own a power plant, what you wouldn't want to see. So this particular component is called a transition piece, and it's what transitions from a round combustor. So this would be a can combustion system. So you have a bunch of cans, round cans, but you're going to go into the turbine, which is an annular. So this is round. This is a transition piece from a round combustor exit to the annular turbine inlet. And that is a big hole that was caused by very large, just imagine that combustion instabilities are causing really large amplitude vibrations, plus it's hot, really high thermal stresses. So that chunk went through the turbine. That's a $10, $20 million chunk that went through the turbine, that little failure right there. So anyway, that's combustion instabilities. Another interesting one, I've alluded to this, is Turndown. So this is a plot of the power generated by a power plant in the United States. I don't remember which one, but it's load as a function of time. And this data is probably, I don't know, 6, 7 years old, because the world is a little bit different than where this data was taken. But what's interesting is, what you can see is, if you just look at days, you can see it's getting turned on. You can see it's basically getting turned on every morning is what's really happening. It's getting turned on, power goes shooting back up, it kind of dwells here, and then it shoots up. But mostly you can see it's running between about 80 and 100% power, then they shut it back down, and they turn it back on. So this is a huge power plant. So I'll just tell you that the heat recovery steam generator on one of these power plants is the size of this building, all right? It's massive. This thing was designed to run 365 days a year, 3 years straight. Turn it on, run it for 3 years, shut it off, clean everything up, turn it back on after a couple weeks. They are actually taking this enormous power plant, they're turning it on in the morning, shutting it off at night. So massive thermal cycling. Well, why are they doing that? They're doing that, this power plant, like I said, this data is about 7 years old, and that was before the price of natural gas in the United States, actually globally, has really dropped because of this shale gas revolution in the US. And so when this power plant was operating, what happened was the price of natural gas made it uneconomical to run at night because the price of power dropped. All right, price of gas is high. They would lose money because the price of gas was more than the power, the electricity price. So they have two options. They could idle this system. They could, turn the power way down. Let's just say you idle it at 5% power, just enough to keep the engines warm. So you're not cycling this thing and causing all kinds of stress. The problem is that this engine can only turn down, you can sort of visualize it, it's not going to go much below 60%, you can see from these. And the reason you don't see it really running below 60% is that below 60% power, it goes out of compliance on CO emissions. We'll talk about CO a little bit later. And so you have a choice. You can only run between 60 and 100% power, or you shut the thing off. So this whole issue of turndown, it's really interesting because it's this balance of flame stability, carbon monoxide emissions, and turndown. So an enormous amount of effort has actually gone on lately in designing these big power plants so that they can turn down to 20% or 30% power, that you can actually just run them continuously like they were designed to be operated without losing your shirt by running at night. But that introduces some combustion challenges that I'll get into a little bit later. And by the way, the reason for a lot of this is that the overall landscape for power generation has changed a lot. And I'll get into that in this next slide, is because there's a lot of renewables, there's a lot of wind and solar on the grid nowadays, and those are usually dispatched first, and so the power plant is usually following those. So in fact, this next slide shows the power generated by a power plant as a function of time. Now instead of days, it's minutes. You can see it's bouncing around all over the place. What's happening is this particular power plant is basically following renewables. And renewables are non-dispatchable, right? You don't tell the sun how much power to give you, or the clouds how much cover to give you. You get what you get. And so you're getting this non-dispatchable dispatching of power onto the grid, but at the end of the day, you got to match. The electrical grid is the supply and demand have to match every instant of time, and so the power plant's making that up. Yes, sir.
So are aeroderivative gas turbines more popular because they can be turned down quite a bit, right?
Yeah, so you'll see lots of things. You'll see aeroderivatives, but even simple cycles are being popped all over the place. And it just depends on time scale. But yeah, but aeroderivatives do have really fast transient response, and they're oftentimes used for load following. But what's happening is that making sure that as your power is swinging around here, avoiding blow off and flashback are really key issues. Because not only, it turns out that when you're generating power on the grid, not only do you get paid for the power you put on, there's a whole host of what are called ancillary services. So some power plants, they make money by just sort of helping do grid frequency stabilization. All they do is they make sure that the grid frequency stays at 60 hertz, and you get paid for that. But it means that you have to have more rapid transient response. But you can only change your power so quickly because otherwise your flame will blow off. And actually, this is a plot that shows it. So blow off, I've referred to this already. This is my favorite picture of blow off. This is an SR-71, which is a very fast experimental aircraft. And you can see that the flame has left the building. Right? That is not where the flame is supposed to be. It's not generating thrust. The flame is leaving the building right here. But what caused this particular blowout was a really high G turn. And the G loadings actually get so severe, these aircraft, that they distort the fuel flow rates, and so you can blow off. But what's interesting is this is an interesting one. This is the North American Electric Reliability Corporation. This is an industry advisory, and they're talking about a grid fault in Florida, and they say indications are that 6 combustion turbine generators within the region that were operating in a lean burn mode, which you all, being combustion people, know what that means, and they even give you this helpful explanation, used for reducing emissions. They tripped offline as a result of a phenomenon known as turbine combustor lean blowout. So what that did was it led to a grid fault. So when I see this stuff, I cut it out of the newspaper right away because my nerd combustion words don't show up in NERC advisory very often. So this one was an interesting one. So let's talk about another one, auto ignition. So we've talked, let's just flip back here. We talked about premix systems. Now, when you premix, it goes without saying to premix, you need time to premix, right? You got to have some distance for premixing if you're going to make a low NOx system. Well, what that means is you have a mixture that is very flammable, but you're saying, but wait, don't burn yet. Wait till you get into the combustion chamber, right? Well, now let's go back to this picture here, whether you're over here or whether you're over here. And we've just talked about how, if you're a simple cycle, if you want to do better thermal efficiency, you want higher pressures, right? And what do you all know about ignition time, auto ignition times, how they scale with pressure? They go down, right? They roughly is 1 on peak. So if you go from 10 atmospheres to 50 atmospheres, you just dropped your auto ignition time by a factor of 5, right? So think about a modern aircraft, and what also happens when you're pressurizing the air, not only is the pressure going up, but the temperature is going up, right? So think about General Electric. These guys are awesome. They're incredible engineers. The modern, let's say a 787 engine, a GE90, it is it's running, let's just say, at 1400 degrees Fahrenheit, 55 bar, running Jet A. You're blasting the fuel in the air, and that stuff really wants to auto-ignite. It really wants to ignite very quickly. So there's an enormous amount of engineering and design that goes in to not auto-ignite, because if it does, you get things like this. This is some hardware from Siemens, but this is where the flame was sitting on hardware not designed for the flame. But again, it's a real challenge as you're going up in pressure and temperature, but also it's a real challenge when you start getting higher hydrocarbons in your fuel, because as you go up in higher hydrocarbon content, auto ignition times drop. So actually, somebody mentioned this, poor control of dew point. This is an interesting one, because as you add, let's just say, propane or butane to your fuel, let's suppose that propane or butane might be 3% in your fuel. That's not going to have a big impact on auto ignition times, okay? But suppose now that I run my natural gas through a valve to control the valve, right? I got a control valve. So how many of you know about Joule-Thompson cooling? So Joule-Thompson cooling, is a non-ideal gas effect, but basically when you throttle a gas and it's not an ideal gas, you can reduce the temperature. And what that can do is, so now you take natural gas, now the temperature just plummets because you just ran it through a nozzle. What can happen is that propane will drop out and it'll become a liquid. So you get a liquid droplet in your fuel flow. So you have a fuel that's nominally 2% propane, but in reality what it is it's binary. It's either 0% propane or there's little droplets that are 100% propane. Now 100% propane auto-ignites really easily relative to natural gas. Hundreds of degrees lower, it's much easier. Those can act as little catalysts. They go bang, they pop, they auto-ignite in your premixer, and then once they go, they take everybody with them. And that's actually what happened here. When they talk about poor controlled dew point, what they mean is that you really have to spend a lot of time designing your whole fuel metering system and modeling all those non-ideal gas effects to make sure that you're always making sure that you don't get liquid dropout in your fuel. All right, let's talk a little bit about emissions now. So that's my constraints and metrics section. Let's talk about emissions. So this will be very, very quick because most of you will know this stuff. So first, if we talk about NOx emissions, so NOx, it stands for nitrogen oxides. So we have NO and N2O and NO2. And I think, obviously there's an enormous amount of really interesting kinetics that goes on with NOx chemistry. But sort of from a zeroth order, you can think of, you have flame NOx and you have post-flame NOx, right? You have NOx that's formed where, in fact, the fuel is actually reacting with the nitrogen in the air to form NOx, right? And here I'm talking about systems where there's no fuel-bound NOx, where the NOx is in the air. You also get post-flame NOx, and this occurs when you take nitrogen and oxygen and you heat it up above, we just said about 1800 or 1850 K. If you just take nitrogen and oxygen, you heat it up, the N2s and the O2s will start reacting with each other, and they will start forming NOx. And so kind of a simple formula is for a given fuel is NOx is going to be A plus B times tau residence, where A is the flame NOx, tau residence is your residence time, and B is sort of the post-flame NOx sensitivity. And so post-flame NOx is generally called thermal NOx or Zeldovich NOx. And again, the idea is once you heat that air up, it's just going to spontaneously react. And so if you give it 10 milliseconds, it's going to form a certain amount of NOx. If you give it 20 milliseconds, it's going to form twice as much NOx. So that's the residence time issue. And then you also have flame-generated NOx, and there's a variety of different mechanisms by which NOx can form in the flame. And somebody already pointed out that as you have more higher hydrocarbons in your fuel, you get more flame-generated NOx. Let me just jump over that. But so let's talk about thermal NOx for a minute. So this is the Zeldovich reaction, and really this is the kind of the key initiation step. Is you have nitrogen N2 in your air. So how does N2 go to air? Well, you got O's, and where do O's come from? This is a combustion radical, right? When you have combustion going on, you have O radicals floating around in that soup. Those can react with N2, those form NO, but they also give you an N, and then once you have the N, that can react with O2 to give you NO plus O. And this rate initiating step here, this initiating step is very temperature sensitivity. This is the reaction that really doesn't take off until about 1800, 1850 K. And so this reaction rate increases exponentially with temperature, and also because your NO levels are so much below equilibrium. Equilibrium NO levels at flame temperatures are in the thousands of parts per million. So if you gave it all the time in the world that it wanted to form NO, you'd have a couple thousand ppm. But you don't. You have a certain amount of residence time, so NO levels are way below equilibrium, and so therefore NOx formation is pretty much linear with time. So if you take a combustor that's 1 foot long, you'll form a certain amount of NOx. If you make it 2 feet long, you double the residence time, you'll form double the NOx. Obviously, if you just keep making it longer and longer, as you approach equilibrium, the linearity relationship won't hold. But almost always, you're so far below equilibrium, you're basically linear with residence time. So you have a reaction rate that's increasing exponentially with flame temperature, linearly with time. And so this is kind of a standard, this is some very standard classic data that was taken by General Electric, plotting NOx as a function of flame temperature. This is a log scale, just showing the exponential increase of NOx emissions with temperature. This is the thermal NOx. And so, kind of the point there is that, if you want low NOx at a given residence time, lower the temperature is better. But what they also have are lines that show mixing quality. So the idea here is that this is if you really, really have nearly perfect premixing. So if you could, and that, by the way, gives you a pressure drop, right? If it means that better mixing means it's going to take more pressure to shove your fuel through these. You're going to need smaller orifices, more distributed fuel. more turbulence, and all that stuff gives you pressure drops, which gives you a cycle efficiency hit. So good mixer, poor mixer, what that shows is at a given sort of average temperature, as you drop mixing quality, NOx emissions are going to go up because obviously you're going to have locally, if it's bad mixing, some regions will have high fuel air ratio, some will have low. Overall, temperatures will be higher. And so that motivates this fuel lean operation. It's sort of the standard strategy in dry low NOx combustion system because of results like this. Let me jump past that. And this just demonstrates the same basic idea. This is a plot from Chemkin showing NOx formation rates at 15 atmospheres and an inlet temperature of 635 K. This shows NO as in parts per million as a function of resonance time. And this is at different fuel air ratios to give you different adiabatic flame temperatures. So 17, 1750, 1800, 1850, 1900. So you see this pop initially, that initial jump is largely flame NOx, right? That's the NOx generated in the flame zone itself. And then you have this linear rise. So this is the A and this is the B times tau. So the longer the time is that you're at a high temperature, the more NOx you're going to form. And obviously the higher your temperature is, the higher this sensitivity is, right? So at 1700 K, you're below that magic 1800 K number. You get a little bit of flame NOx, but this curve is pretty flat. Once you start to get above about 18, you can see at 1850 K, this curve starts to take off. And like I said, in many regions in California, NOx regulations are at as low as 3 ppm. Many regions in the US are 9 ppm. These are state. And then from the US Environmental Protection Agency sets a regulation of 30 ppm. That's sort of the national standard, but then there's lower level local standards. The World Bank, which in order to loan money to a developing country to build a power plant, their number is 30 ppm. So that kind of gives you some context for, well, if you want to do 30 ppm at 1850 K, well, you're going to have to keep your residence time below, I don't know, 75 milliseconds or something like that. Yeah?
In the previous slides, you have mentioned
So those are the prompt NOx that's formed in the flame. Those all kind of combine to give you that bump right there. So this is basically Zeldovich NOx or thermal NOx, and this is NNH, N2O, NO2, etc., those flame NOx mechanisms. In many cases, Zeldovich NOx is your dominant NOx producer.
also like for measuring NOx, in Europe you have EI NOx.
Right.
What's the difference?
Well, it's just for aircraft engines, you also use EI. Yeah. I just chose to use ppm here, but you're right, just depending on where you are. So EI is generally NOx, kilograms of NOx or grams of NOx produced per kilogram of fuel consumed. Yeah.
Question, is the spread with flame temperature as strong if the NOx is referenced to 15% of
Yeah, this is all 15%. Yep. Yeah, good question. I didn't put that, but this is all corrected to 15% oxygen. But you can see at 1900 K, it's really starting to take off, and sort of the current state of the U.S. government has a goal. In fact, they have some programs they're awarding to design engines with 1975 K. So add another, so you can kind of imagine at 1975 K, this curve is going to be even higher. Well, really high. This is 1800, that's 1900. This curve's really going to take off. Well, so what that means is in order to if you got a 9 ppm limit, for instance, at 1900 K, that means your residence time's got to be less than 6 milliseconds. So that means all the action's got to happen. Your flame's got to be within a 6 millisecond residence time. Well, why is that a problem? I'll talk about that in a minute. Let me jump over these slides. Well, let's talk about CO for a minute. Now, as I mentioned, NO and CO are fundamentally different in the sense that equilibrium NO is in the thousands of ppm. You start out with 0 NO, and you're basically climbing towards equilibrium, but you usually don't get there because what happens is you quench, right? Combustion's done, you go into the atmosphere, and you cool off, and NO formation rates freeze. CO is different. So as you've probably learned in other classes, the way fuels turn into products, let's just say methane. So this is a plot showing mass fraction as a function of distance through a laminar premixed flame. So here's methane, here's CO2, there's H2O, this is temperature, this curve right here is heat release rate. So what happens is methane basically gets turned into synthesis gas, right? So methane decomposes into hydrogen, so here's hydrogen, and CO, that's CO. So you have hydrogen and CO. So methane forms hydrogen and CO, and that's really step one. So a simple two-step conceptualization of how CO is formed is, step one is the fuel reacts to form intermediate species, hydrogen and CO. And this is true not only for methane, it's true for pretty much any hydrocarbon fuel. As you have the hydrocarbon, it decomposes into hydrogen and CO, and then you get step two is hydrogen then reacts to form water, CO reacts to form CO2. That's step two. Well, you get CO if step two doesn't happen, right? So if all that CO, you're forming a massive amount of CO in the flame, right? So look at this number. This is CO. So for this particular example, this would be about 27,000 parts per million of CO. You know, you're going to die if you're, 200, 300 parts per million of CO, you're going to get a massive headache and die in an hour or something like that. 1,000 ppm of CO, you're going to be throwing up and die really fast. So in the flame, you got about 27,000 parts per million of CO. But the CO then goes away. And so as opposed to NOx, which starts at 0 and rises towards equilibrium, CO is falling towards its equilibrium value, right? And so how do you form minimum CO? Is you give the combustion lots and lots and lots of time for that CO to get towards its equilibrium level. So who can see the conflict? NO, short times, because CO is rising towards, NO, short residence time, it's rising towards equilibrium. CO, it's falling towards equilibrium. So there's this inherent tension. Standard trade-off, NOx-CO trade-off in systems. And this just shows that in a little bit more detail. It shows CO as a function of residence time. And so you can see this spike in the flame, and then you can see it falling towards equilibrium. So a couple things that you can notice is going on here. So first of all, you have 10,000s, sort of on the order of 10,000, 20,000 parts per million of CO in the flame, which is why you can kill yourself, right? I mean, if you quench a flame, or when you have incomplete combustion, it's a quick and dirty way to kill yourself. But it drops down. What's interesting is that as you go lower in temperature, equilibrium CO is lower, right? So you have higher equilibrium CO at 1900 K than at 1500 K. Does anybody know why that is? Well, because where does the equilibrium CO come from? Well, because there's always a certain back and forth between CO going to CO2 and CO2 coming back to CO, right? And so as you go up in temperature, you get more dissociation of CO2 back to CO. So that's why equilibrium levels are higher at temperature. But what's interesting is, imagine that I have let's just say a 20 millisecond residence time combustor, all right? And I'm dropping my flame temperature. So I start at 1900 K, I drop my flame temperature, 1800 K, 1700 K, 1600 K, 1500 K. CO just took off, right? Because what's happening as you drop temperature, although equilibrium levels are lower, it takes longer and longer and longer to reach equilibrium. Which is why I mentioned before, turndown is always limited by CO emissions, because basically when you turn an engine down, or you're basically reducing fuel-air ratio, you're reducing flame temperature, and it takes longer and longer and longer for that CO to oxidize to get to equilibrium, and at some point all of a sudden CO just takes off. You get monstrous, and that's basically going to be as far as you can turn your engine down. So I gave you that example where I showed the power plant where it just would not operate below 60% power, and below 60% power, CO would take off. What was that? The what condition? I don't know the answer to that. It's a good question. There's aerodynamic issues with the aero engine as well. related to RPMs. You're going to have separation. So I'm not sure whether that's a combustor issue or a turbomachinery issue. Mm-hmm. Oh, okay. Okay. Thank you. So actually, this just shows the same thing that I told you. This is CO parts per million as a function of equivalence ratio. And you can see that, and this is different pressures, 100, 200, and 300 psi. And you can see CO is dropping as you're dropping equivalence ratio. So this is basically equilibrium controlled. And then you can see it just takes off. So there's this wall below where you can't operate because your CO levels will go out of compliance. And so what that leads to is this NOx-CO trade-off, is that you want long combustors for low CO emissions, short combustors for low NOx emissions. So really interesting stuff that happens there. I'm just going to jump over these, but let me just show you this slide because I referred to this. There's some really interesting NOx and efficiency trade-offs which we're now starting to encounter. I mentioned how in order to make, let's just say, a combined cycle power plant to make its thermal efficiency go up or to reduce its CO2 emissions, you want the turbine inlet temperature to go up. So this is a plot of flame temperature. And so as you go up in flame temperature, you're increasing cycle efficiency, all right? And but we also know for a fixed residence time system, as you go up in flame temperature, you're increasing NOx. So this is a simple calculation from Chemkin for, I don't remember, it's like a 20 millisecond, a flame where the combustion products are at 20 milliseconds. And it shows you how NO varies with flame temperature. And what I've put on here is just different classes of engines. This would be older technology, newer technology, really, really new technology, and how it's going up in flame temperature. What I also have here are some lines just showing some different NOx emissions. So sort of the range in the United States is between 3 and 30 parts per million. This is the range in Canada. This is the World Bank number. But what you can see is that let's just say you have a 30 ppm limit. Well, for older engines, NOx was a non-issue, right? You could go up in flame temperature and that would give you better cycle efficiency and you were still way below NOx. But now as we're starting to get up around 1900, 1975 K, you're starting to get into a world where you simply are making a horrible lot of NOx. And so now I think this is a great combustion problem, is how do you turn off Zeldovich? So those of you who are doing high pressure, high temperature kinetics, what is it that you can do to somehow fundamentally change that sensitivity to temperature? Because, all right, well, let me just tell you, let's suppose I got to run at 1975 K. You'd say, well, given the world that I live in, I'm going to be at 20 millisecond residence time, I'm going to make about 50 or 60 parts per million of NO. Well, one thing you could do is you could reduce residence time, right? You can make the combustor shorter. And that is a strategy. What's the downside? Turndown, right? You made an engine that turns down worse than the original engine. Because at part load, since it's got even less residence time, it's going to go bombing out of CO compliance even earlier. So this is a really interesting issue, and I think it's a great combustion problem that I would bet that many of you in this room will be working on over the next decade. Is the turbine people kind of threw down the gauntlet. We didn't have to worry about NOx for a while. All we had to do was mix better. But now we got to say, okay, even in the limit of perfect mixing, we're not good enough. So it's a really cool problem. Let me just say a couple things about auto ignition now. I've talked about emissions, and I'm blitzing through slides because I'm taking too long to talk. But let me talk a little bit about auto ignition now. And as I mentioned, in premix systems, premature ignition is a very significant concern. But also, there's other in explosion problems, auto ignition is an issue. And so let's go back to this picture that I showed you earlier of NOx as a function of flame temperature. So let's suppose that you have a given flame temperature, which is set by your cycle. What this shows you is that you want better and better mixing reduces NOx. Well, how do you make a better mixer? Well, you give the fuel and air longer time to mix, right? And so, but if you give the fuel longer to mix, that means that you're giving the fuel and air more and more time to auto-ignite in your mixing passage. So there's this really interesting trade-off between auto-ignition and getting good premixing for NOx reduction. And sort of the major point I wanted to leave you with is that this is an explosion diagram. You'll have all seen this before. You've seen the explosion diagram for hydrogen, which has got the interesting S curve. This is the explosion diagram for methane. And if you're in the upper right corner, you're going to explode. If you're in the lower left corner, you're not. And it just shows you that propane auto-ignites a whole lot easier than methane. And in fact, let's just jump ahead too. This plots the auto-ignition temperature as a function of carbon chain length. This is methane. It auto-ignites at about 540 C. Ethane drops. Propane drops. The whole point is, as you get more and more higher hydrocarbons, the easier it is for the mixture to auto-ignite. And then as you start looking at things like jet fuel, which would be decane, C10H22, you can see how much easier jet fuel auto-ignites than liquid fuel, which is why sort of lean premix designs entered the world first in the power world than in the aircraft engine world, because in the power world you generally use gaseous fuels composed primarily of methane. And so it's much easier to make a system where you can get good premixing between the fuel and the air. Whereas in an aircraft engine, or if you're using liquid fuel, this stuff auto-ignites super easy. So you're trying to take the stuff, and it's going to be a liquid generally at your conditions. You're going to need to vaporize it, mix it, and that's all got to happen. And your temperature is potentially well above this temperature. So you might have fractions of a millisecond before the mixture auto-ignites. So it's a really, really tough engineering challenge as we start looking towards, and as we go to higher and higher pressures for systems that use liquid fuel. Okay, and yeah, I'll just jump past that. Let me just highlight a couple other interesting, what I would just call future outlook for needed research. And in particular, this whole issue of CO2 constraints. An interesting question is, what's the role of combustion in a world with low CO2 emissions? Is everything going to be is all the power going to be generated by solar and wind? It's an interesting question, but in fact, there are a lot of really interesting combustion challenges in a low CO2 world, even in a zero CO2 world. All right, and so we can talk about those. So as we said, CO2 emissions are going to be set either by your fuel or by your cycle choice. So for example, a cycle choice, if you're burning a hydrocarbon, you're going to make CO2, nothing you can do about it. The job of the combustor is to make CO2, right? So how do you minimize CO2 emissions in a system that's burning a hydrocarbon? Well, you have a higher efficiency cycle, okay? Which means higher pressure. It could also, yeah, that's why I said that. Sorry, I should read my own stuff. High pressure combustion. It also means that you could potentially capture the CO2 from the exhaust stream. All right. Well, how do you do that? Well, one way. So there's lots of work going on in separations and things like that, but you take an efficiency hit when you start pulling CO2 out of the exhaust stream. So you really want to increase the concentration of CO2 in your exhaust stream. Well, one way you do that is you use exhaust gas recirculation. So you recirculate the gas. So exhaust gas recirculation starts to become an interesting question. And this is interesting because CO2 and water, when you recirculate those back, those are not chemically inert. They're not like nitrogen, which is basically an inert. CO2 is very chemically active. In fact, at Princeton, Yiguang Zhu, a professor here, he's done a lot of work on how you can start to get interesting radiative interactions between products and reactants. So air is pretty much translucent to radiation at combustion pressures, whereas CO2 is not. And so what can happen is the hot combustion products can radiate back. And so you can actually have heat transfer by radiation, not just by conduction, back to your reactants. So that's an interesting problem. So coming back to carbon capture, pre-combustion carbon capture, what that means is you pull the carbon out of the fuel before combustion, which means your fuel is hydrogen. So high hydrogen combustion is really, really interesting. We've done a lot of work in this in our own lab. And so if you take all of combustion, Hydrogen is, it's like its own animal. It's like if all of combustion's a cat, high hydrogen's a dog, right? It's just the molecular weight difference between it and everything else is just so profound that hydrogen just acts as a completely different animal. Just think about flame speeds. You know, the flame speed of methane is different from ethane. It's a little bit different from decane, dodecane, etc. But those are, you know, what, 20, 30% differences. Whereas hydrogen, it's an order of magnitude, right? The flame speed of hydrogen is an order of magnitude. Or the molecular weight difference, which affects stretch sensitivity, which we'll talk about later. Post-combustion carbon capture, that's where you pull the CO2 out after. And in that case, when you do that, you want, this goes to the EGR, which I already talked about, where you want to crank up the CO2 levels in your exhaust stream. Or biofuels, if you want to have and this says biofuels, but this could also be synthetic fuels, because the idea is, suppose that you generate a hydrocarbon synthetically. It could be using a Fischer-Tropsch process. So, for example, if you take carbon monoxide and hydrogen and you run it through a catalyst and you generate a synthetic diesel or a synthetic kerosene, you know, this is already done. It's been done, and for example, South Africa does this to generate jet fuel. If you've ever flown from South Africa, you have flown in a synthetic hydrocarbon. It's a synthetic jet fuel generated in that case from coal, highly non-CO2, but it's the same basic process. You take coal, you gasify it, you form CO and hydrogen, you run that through a catalyst, and then that forms a synthetic fuel. And now imagine that you are using a renewable fuel. Let's just say you have a wind turbine, and one of the big problems with wind turbines is the wind blows the most at night, which is when the load is the lowest. So how do you store wind energy? Well, there's a lot of talk about batteries nowadays, right? Using batteries to store that wind energy, and then you dump it on the grid during the day. Another battery is a fuel, right? So there's a lot of people talking about, well, why don't you make hydrogen at night, and then you can burn the hydrogen in a fuel cell or in a combustor during the day. Alternatively, what you could do is you could generate a synthetic hydrocarbon, and you could just be making synthetic diesel, synthetic kerosene, whatever, and then you'd be burning it. So you can certainly generate zero CO2 hydrocarbons, and there's a lot of, not in the US, but in the European Union, there's a lot of research going on synthetic zero CO2 hydrocarbons. The benefit of a synthetic hydrocarbon, as opposed to using hydrogen as a fuel, is that we don't have a hydrogen economy, right? You know, you've probably heard the word hydrogen economy. Well, guess what? There isn't a hydrogen economy. There's a few gas stations around California, and there's a few pipelines here and there. But by and large, we don't have a hydrogen economy. On the other hand, we have a natural gas infrastructure. We have millions of miles of pipelines for moving gasoline, and so that's why there's an interest, is it's almost plug and play. If you could just take renewable fuels and you could leverage the existing infrastructure. All right, I think, well, I think I'm just going to skip these because I went too long. But let me just wrap up this last section, which is there's lots of really interesting challenges associated with steady flowing combustion system around fuel flexibility. I've talked a little bit about that, but as you look at future fuels, renewable hydrocarbons, synthetic hydrocarbons, biofuels, things like that, balancing air quality emissions and CO2. I gave you that example. I talked a little bit about how we're now at the point where if we want to go higher efficiency cycles, in other words, lower CO2, we're going to have to rethink NOx. What does a low NOx architecture think about? Operational flexibility, so a world where there's lots of renewables on the grid and you need to be bouncing power all over the place and having systems that can have really fast transient response. Reliability, and then also low cost. This isn't really, obviously this is an engineering, a practical concern, but this flows back into physics. And the physics question is, how do you make a premix flame that's intrinsically more stable? You know, is that plasma stabilization? I don't think anybody here is doing this stuff, but lots of questions around, rather than having to have, let's say, 6 fuel nozzles and 3 fuel circuits in a modern premix system, it costs 10 times as much. Instead of costing $100,000 for a nozzle set, it costs $1.5 million for a modern power plant. How do you just build the physics in such that those flames, that you can run them over this big range of fuel-air ratio so that you don't need the more expensive solution? So anyway, lots of interesting physics there. Anyone have a question? So let's start, let me just start the next section, and we'll take a break here in a minute. All right, I want to talk about, flame aerodynamics. So that's kind of the problem I want to talk about, which I introduced already. And I also want to talk about this within the context of flashback. And so flashback really is, and it's a very important applied problem. Basically the question is, if you take a flow where the velocity is higher than the flame speed, higher than the turbulent flame speed, what are the mechanisms whereby a flame can propagate upstream? Okay? So obviously, if the flow speed is not higher than the flame speed, the problem's trivial, right? Because the flame can just shoot upstream. But what makes life interesting is to say, well, what are the mechanisms by which a flame could actually propagate upstream in a flow where the velocity is everywhere higher than the flame speed? That's really the problem of a flashback. So let's talk a little bit about this. And really, there's three basic mechanisms that lead to flashback. You can have flashback in the boundary layer, right? So in the boundary layer, the flow velocities go way down, and potentially, if your flame speed doesn't fall faster than the flow velocity, you could potentially have a flame shoot upstream in your boundary layer. You could potentially have flame propagation in the core flow. So in the high velocity core, the question would be, how could the flame propagate upstream even though the flow velocity is everywhere higher than the flame speed? And I'm going to show you a mechanism, really interesting mechanism, that if you have swirl in the flow, there is a mechanism whereby the flame can propagate upstream. And then finally, you can have combustion instabilities. And I'm just going to mention this for completeness, but I'm not going to dig into it. But the idea is if you have really large amplitude pulsations, so let's suppose that your average flow speed is 50 meters per second. Well, it's going to be really hard for a flame to propagate upstream into a 50 meter per second flow. But suppose the flow is oscillating in such that instantaneously it's oscillating between 25 and 75 meters per second. Or even if you really get a violent thermoacoustic instability, the flow can actually reverse itself. So the flow is actually going backwards. So it's actually going negative, maybe negative 10 meters per second. It's sucking the whole flame upstream. And when it gets sucked upstream, it starts melting stuff. So the problem of combustion instabilities and flashback is very, very much coupled. And the significance of these are really interesting problems because they have different sensitivities to your fluid mechanic features, to your fuel composition, to your operating conditions. So for example, pressure. Let's just talk about pressure. How do you think pressure is going to affect flashback in the boundary layer? How come? So pressure certainly affects the boundary layer thickness, which is what you're saying, right? So as pressure goes up, boundary layer gets thinner by what? Square root of Reynolds number? I think. Let's assume it's square root of Reynolds number. So what's the pressure sensitivity of square root of Reynolds number? UD over nu is Reynolds number. What's the pressure scaling of nu? 1 on P. Reynolds number scales linearly with pressure. Okay, so if your boundary layer thickness scales square root of pressure, if the boundary layer thickness scales as the square root of Reynolds number and the Reynolds number scales as pressure, what that means is the boundary layer thickness drops as the square root of pressure. Okay, so you're right. But what happens to the flame as pressure goes up? Flame speed goes down. Flame speed goes down.
The thickness decreases.
Thickness decreases. Yeah, and that's the $1 million observation there because because remember there's this quenching distance idea that if the flame, there could be a region where the flow velocity is really low, but if the flame gets too close to the wall, it's going to quench. But as the flame gets thinner and thinner and thinner, that effect, what's close to the wall is going to be a function of flame thickness units, right? So if the pressure goes up by a factor of 10, flame thickness roughly scales as 1 on P. Boundary layer thickness scales as 1 on square root of P. So in fact, going up in pressure makes flashback easier because the flame thickness effect. The flame thickness effect wins. It's a pressure, it scales linearly with pressure, whereas the fluid mechanic effect scales as the square root of pressure. But I'm glad you said that because it just shows the subtlety. There's fluid mechanics and there's combustion, and they're talking to each other, right? They're interacting. So let me just show you a couple little videos here. So the left side is sort of a macro view of the combustion system, all right? And you're looking at the luminosity given off by a flame. The middle picture is a detail, it's a PIV image, so you're looking at the seed particles. And when you see this, you see no seed, that's because the seed's getting burned up as it's passing through the flame. So this interface is telling you where the flame is, all right? This is a detail of the, let's see, where's the flame flashing back? It's flashing back, I guess, down this wall right here. This is a really, I think this is that wall right there. This is a detail of that. This is the luminosity of, or excuse me, OH pliff. And so this picture and this picture should nominally correspond. So what's happening here is you're seeing boundary layer flashback. The flame is propagating down in the boundary layer, and there you see the luminosity given off by it. So let's do it one more time. Here it comes. Flame's coming down. There's flashback in the boundary layer. We'll talk, and I'm going to show you some more details of this data in a little bit later. So that's an example of a flashback in the boundary layer. Oh, come on. All right, I forgot my quick keys here. How do I flip back to my presentation? Tell you what, it's 4:15. Why don't we take a break, and we will reconvene at 4:30.